Okay, Advent of Code 2025 day 1 recap with K1 programming. So I recorded a few sessions working on this. I'm not too proud of them, but I will upload them. They'll be at the end of this video. But I thought I would do a walkthrough of the solution and kind of the language and some of the highlights here to make for a bit of a better video. So the puzzle is I'll leave it to you to read it offline. Essentially, you have a spinning dial like on a safe, and you're trying to detect how many times it hits zero, lands on zero, or passes zero as you do a series of instructions. So your input looks like this: rotate counterclockwise 68, rotate counterclockwise 30, rotate clockwise 48, clockwise 5. You probably get the idea. So we do a little parsing, not a lot, and then simulate this thing and sort of track the simulation as it goes. So it's not about the end position of the dial at all. It's about the number of times it passes zero. Actually turned out to be a really interesting problem with tons of edge cases, very edge casey. And so, especially in part 2, it's pretty interesting. But I thought I would highlight more as it pertains to the language and how it went. One thing is encountered no major bugs, so I was able to just sort of program it. I did have to implement string/parse base 10, which I did during the session, in order to parse these decimal strings, which I actually haven't ended up having to do yet so far. I go the other way a lot, formatting integers, but I don't think I had a function like that laying around. So we added that. Absolute value, we also added as a helper, not too hard of one, but we did it the bitmask way. So that was interesting. And I also struggled quite a while to get the correct count here, and I think that the method I was using was just a challenging one, so I ended up going back to just applying the entire change, even if it was greater than 100, and then managing the sort of the side effects and the edge case of the start on zero later. And this works, and this version will solve part 1 and part 2 by counting SZs as stop zeros and MZs as moving zeros. It's really part 1 and part 2. So we could do MZs. It's fine. Part 2. Part 1 count. We'll just do that. So what's interesting here? So function main, we have an LSP server running, which is kind of fun here, and just prove we have our LSP log. So things are running. We've compiled twice since opening this file. I got up to so let me do a save and a couple, and then we'll reload. There's 4 times. So I got up to 200 in one session without a crash, which was really nice. And I did also implement a brute force solution where we move the dial 1 tick at a time and then check the position to get a baseline, and because I was super stuck. So we actually don't need input can just come from the static. Yeah. All right. So here's the brute force method. It's the same parsing and setup, and then we just do another loop for each command where we just move the position by literally 1, apply wraps, and increment. One's the most straightforward to understand, and then we have the fast one, and we'll time both of these, runtime and compile time. So here's the sample string. Got to use my multi-line strings with a backslash. If you have a backslash, then you can do a lot more things unescaped. So that's nice. Let me clear this out because it's ugly. All right. And what I'm doing here is I'm actually reading in the file to a global. So you may notice this line is not inside a function. So this is a low-level programming language. Although my goal is for it to be both high level and low level. So when does this code run, right? And the answer is this code runs at compile time. So this gets compiled to bytecode, and we execute the function read to string as our bytecode, and then anywhere there's a syscall or a libc call, we use libffi to actually run the function. So this actually does like an fopen, an fscan, fread, fclose, all that stuff, and then we end up with a compile time known constant string that does end up in the final binary, which I can go ahead and show you. So we have in our outdir day 1 dot we'll do the LOVMIR. We can come down here past some of the common constants, and well, yeah, okay. So here's our sample, and the strings aren't named. There is going to be one called at sample. Right, here's sample. The thing is, it points to that string data. So we do get one called sample. It's just the length known one. It's a K1 string. But yeah, here's the sample string, and then here's the puzzle string. So it's 1,946 bytes. Is it? It is 19K. So that's kind of cool. You don't have to load a file at runtime. How long does that take though to do at compile time? It takes a little bit. So we don't need this allocator. This is warning me that it's unused because we're no longer allocating any memory because we're doing this. So if I were to load the input at runtime here inside the function, then and not manually just specify an allocator, then this warning goes away. But let's leave it at compile time and let's not specify it. So how does this look? We input is a string, right? That's our file. We say split by char n. This is a 0 copy splitting. This is just because our strings are slices, right? Like just pointer and length, and they're immutable. This can be, essentially free as fast as you can get, I think, an operation like this, which is nice. It's not an iterator, so we do actually allocate a view of strings because that's typically what you want. I could do an iterator version later. All right, so we initialize the dial, and we say for commands. So this is sugar for it in commands. This is I think the idiom kind of made popular by Jai. I think it was John Below was the first to have this idea. Often you want to just have the default name for the thing, and it's kind of nice because you have this it, and that kind of signals to you that's the main iteree, the main thing we're looping over, which is nice. So I did the shortcut version here. Commands is a string, which means it implements iterator for char. So we can actually search for that, impl iterator. And if we go into some K1 code, let's see, type, scopes, range, blah, blah, blah. Maybe it's for string. Let's try for string. Here we are. So impl iterable, where the item is a char and I is a buffer iterator over chars for string, and we just get a character view, basically like the byte array underneath, and we dot iterator. So the reason this syntax works is not magic. It's because we just wrote this regular code here in string.k1. So anyone can implement iterable. Pretty standard type class based standard library stuff there, but still really nice. So we're going to check if it's an L. We're going to drop that first character, and then now we have a slice of just the magnitude, which is what I'm calling it. We're going to parse that, which gives us an option. And this is like a let else. So here's the thing we call, and then if that is sum, this creates a binding, and then we can use this variable name later. Otherwise, we're going to return. We could print. And then here is times -1. I don't have a great way. This is an unsigned int, so we're going to our standard sized representation because we want to wrap around 0. We want negative values. So yeah, it might be worth annotating this as like this is a signed int, but there we go. We apply the change. Here's the core of the puzzle logic, which I don't really want to spend too much time on. So I'm focusing on the language. Some things could be nicer, like assignment could be terser if we had plus equals. It's just simple sugar. I may end up adding it just because having it's not super in the spirit of the language, but it's not terrible. We're not using last pause except to print, so I could go ahead and put an underscore on that to ignore the warning. And then here we go, and here's brute force. So let's go ahead, let's run brute force at compile time and our other approach at compile time. We'll run them both, and what we're going to do real quick is we're going to make them both crash. So first we'll make brute force crash, and then you notice we got a red underline down here. So if I go to this error, we're going to see if static code crashes or static code returns an error, you get a compiler error, but we also dump all of its output. So everything that it printed while it was running, we're going to see here. So this is my sneaky way of live coding here in the language. We just crash at the end of something we run statically, and we get a diagnostic where we're seeing 7101, and that is our correct answer for day 1. So that's fun. Just wanted to prep my browser there so we can say 7101 and back. So there's the brute force approach. You may notice it takes a little bit of time. Let me remove this and I'll add it back in. So I'll say save, boom. So there is a delay. It takes, I measured 1/5 of a second to run the brute force one thing at a time version at compile time. So now let's go to day 1, and what we'll do is let's make it crash. So we get an error, and I will see day 1, we're not gonna see nearly that same delay. Part 1, these are the correct values for both of these parts. So what's neat is we're able to run this program entirely at compile time. Now this is something you could feasibly run at const time in like C++ or Rust, something without like full-blown execution, because I don't think we're doing any allocations in here, and I don't think that we're doing any IO either. So this is fairly run-of-the-mill, comp time stuff, but the fact that I could read a file, I could allocate, I could make a HTTP call, and it would still run at compile time is kind of the secret sauce here. And we can actually, well, I won't go into that. We could return the solution as a compile time known constant and have the type of 7101 be our expected type of the solution, which would be kind of fun. So anyway, we've looked at the input being embedded. Let's time how long brute force takes to run in interpreted mode, basically, or it's not really in compile time. So we're gonna come here, we're gonna K1, we're only gonna check this module because I want to stop after compiling. So this is check with brute, and let me just time it. And this is going to include parsing and compiling the entire standard library and then the puzzle. So hopefully that's all right. But we see that almost all of the time is in that 0.2 seconds. Let's run a few more. Hyperfine. Can I expand that? Something like this. Can I do this? No, we don't want to time it. Yeah, -I. That's okay. All right, so that's how long it's taken. Let's take a look at the non-brute force version. So now, remember, we're just type checking these files and running the code that's run at compile time. Actually, surprisingly similar. Yeah, with a lot of variance. It could be that we're, dominated by some other things, or that inner loop is quite fast. So I'm kind of intrigued by that. Now let's run for real. So we can run the brute force at runtime, and we'll run. So this time, instead of saying check, we're gonna say run, which is gonna do. We could do build, which will produce the binary and not run it. Notice that it compiles pretty fast. But we'll do build. All right. So and then that produces a binary here called day 1. And now we're gonna run this. Boom. And we got our crashes in here, so let's remove those. Okay. Let's build again. Now let's run. All right. Hyperfine. So nice 9 milliseconds, and that's fun with the file embedded. We could take a look at the LLVM, but you'll see like a standard kind of O3 optimized value. None of this is boxed. This is all normal. This is all just like native register stuff. And yeah, there's going to be no runtime overhead to this loop. So that'll be about what you could expect. And loading the file at compile time. Now, the other thing I wanted to test, let's load the file at runtime. So we'll move input into here for day 1. And that's gonna fail for brute 2. We'll load the file. Input string. Let's do that. And now for brute. This might be better anyway to have been doing it this way. We'll do this. All right, so now we're gonna load the file at runtime. About the same. which, it's not a very big file, and now it's hot in my cache. So, let's check though. LVM des day1.bc, that's going to be the latest one. And then let's just open up day one and see if the big old constant's gone. Yes, we have the sample, and you may notice we do not any longer see the actual puzzle input, the big one, in here. So that's kind of fun. Let's go back to baking it in. Boom. Kind of neat that you can just move that one line of code and you get an entirely different compiler tool chain compiling this code into. I don't think I can do this. Debug. Maybe I can. Have you see? No. I wanted to show the bytecode, but we can save that for another time. So that's my day one, how it shook out in the language, with a bit of a sort of demo of what the language is capable of. If you watch this, I really enjoyed it. I appreciate it. Feel free to like the video, subscribe if you want to see the language progress. Again, thanks so much for watching. See you in the next. Welcome to Advent of Code Day 1, 2025. Cheers. It's the early morning. Very excited for this. Let's see if I have time to do this one. Of course, let's set up our environment first. We'll be using K1 for this, the language. So spoilers. Let's see. So I have a dog food folder inside the project. We'll go in there and we'll actually make a 2025 folder. And we'll just make sure we built the compiler. And let's make a hello world. And we can actually do a bit better than a hello world. We can set up our program to run at compile time, and we can solve the puzzle at compile time. So let's do solve. Let's do day one, and we'll just have it print its result instead. Day one, solution, let solution equals 0, something like this. And now what we can do, we're going to say, I would like to statically run day one. And as long as we make it fail, we'll get a diagnostic message from the LSP, which we can hover, and we see we've printed day 1, 0. We'll print day 1, 3. Then we can have day 1, 3. So we have live feedback now. Okay, so the L's of discovered project management. Oh, we're decorating this year. Okay, the password to the North Pole has been changed. The password is locked in the safe below. The attached document for the new combination. The safe has a dial with only an arrow on it. Around the dial are the numbers 0 through 99 in order, okay? As you turn the dial, it makes a small click. As it reaches each number, rotations, 1 per line, L or R. Okay, Okay, so this is add subtract. Yeah. Dial starts at 50. I believe I understand. The actual password is the number of times the dial is left pointing at 0. The safe is actually a decoy. Okay. So one of the most brilliant things about Advent of Code is that he has to encode the answer as a single integer for every puzzle, and a lot of puzzles aren't very amenable to that, like this one. But he finds a way. Cheers, by the way. I'm not sure that this is going to be the best showcase of the power of this programming language, but that's okay. So they all have a sample, right? We're going to use our backtick strings, which support new lines. All right. We don't need a opening or trailing new line. Maybe this is the convention. 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 Okay, I like that. We're going to call this commands. And I program so little in this language. Split by char is what we want. For commands, all right, so it now prints our commands, but all the white space is in there. Oh, yuck. Okay, those look good to me. Let's print out our position each time. We're going to do an assignment. Let sign. We're going to call it the sign. It. Neg. Magnitude. The magnitude of the turn. Or going to drop 1. Let's just print what we've done so far. Magnitude that we will parse looks pretty good to me. Okay. I don't know how to parse an integer from a string in this language that I have made. NsInt, NSI64, max value, U64. I definitely, do I? Parse. Is this something that we still don't have? So I can do a grep from in here. We have type at K1. We'll do this because this grep gets me dash type K1 parse. Parse main args. I definitely have formatting. I even have formatting with floats. Oh no. Well, they have to be between 1 and 100, yeah. No, they do not. Okay, well, let's just let's parse base 10. Magnitude is 0. Let magnitude equals 4C. I don't think strings implement iterator. Maybe they do. Okay. I think they do. Going to be the first character here, and we can multiply by 10. I guess we must, right? Digit. Maybe I did some of this in the chess program. Well, let's just do it. So 3 is 51. So to get from 51 to 3, we got to subtract 48. Oh, minus 48. I know the number 48. To ASCII digit on a U8. Yeah, see, it's formatting again. It's not going the other way around. To digit value. Oh, that's a single value as a U8. We can at least make use of. Well, let's do it by hand. So we're going to say let digit value. And that will be as a U8. And that's going to be, we're going to say C for character. C, also not to shadow the it from the outer loop. We're going to say C as U8 minus 48. Magnitude, we'll go ahead and just as int. This is a I64, by the way. Okay, so maybe I do use that function. I don't want to re-implement it. To char to digit value. It's an optional U8. We'll just grab it. And that will cast because it's widening. Okay. Times 10. Each time we want to multiply by 10. This is embarrassing. Yeah, and this is the addition. We would want to multiply, the current value times 10. And then the addition will work. Yes. Okay. So here are our magnitudes. Let's pull this out. We don't have any error handling here. Oh, we're actually parsing it unsigned. We'll do sum O. And at each point here, we're going to say if, before we do the int cast, we could have wrapped. If it's not, yeah. If it's, oh, let's just do the range. I think I actually have is ASCII digit. ASCII digit. Yeah, okay. I'm just going to return incompatible integer types. C. Isn't that what I was just doing? Oh, we can use 2 ASCII digit, right? No, that one's... Well... Oh, because that's a char. No, C2U8 minus 48. Isn't that what I was doing above? Oh. I need to improve that. Let me make a note for myself. Incompatible integer types needs info. Whatever that. And now we'll use let sum, let magnitude this will be require sum magnitude unsigned, else return can return unit, I guess. Magnitude unsigned, let magnitude equal if negative So this creates a binding and exits. This is Rust's let else, but it has a lot more nice things, actually. We didn't use them here. Okay. So we should be left 68, left 30, right 48. That's right. Day 1, 0 count. Pause. Oh, it's no longer magnitude. We could have just called this magnitude the whole time. Now we can call this diff. Change. Two zeros. The dial points at 0. Oh, it wraps, of course. So. It's like the entire puzzle is the wrapping. Oh. So, does mod 100 work? It doesn't. Yes it does. Mm-hmm. So each time I could check the bounds and then fix it. I think I might want to do that. $82, $52, 0. Let's stop printing our command. $82, $52, 0, 95. 55, 0, 99, 0, 14, 32, 3. Okay. So this is why using signed integers for math is good. It's nice. I mean, we would have gotten the overflow, like subtract with overflow below 0 thing if we were using Rust unsigned, which might have clued us into like the issue, but I hadn't registered that the puzzle wanted you to wrap anyway at that point. This lets me preserve all the information, right? And I can do math out of bounds and then put things back in. So this works just fine for me. Let's try and read in our puzzle. We need an allocator to read a file to a string. I like to just use the default, the current, unsupported operation free. That's fun. Maybe I'll do that. So trying to do this, all this file IO at compile time is really interesting. I'm gonna see if we can do it though. All right, we have our input. I could just remove the call to free actually. Well, let's try with system heap. Let's get rid of our crash here. Well, we can keep it. And let's just see what's happening here. We're crashing after doing our thing. Oh. Input's never used. Oh, but the LSP is exiting. And I don't know why it's exiting. They removed that command. Can we print out our input at least? Yeah, we can. We loaded the file at compile time using libffi, by the way. The same code reads the string. This is the code that actually runs at compile time. The raw libc calls. Everything just gets called using libffi. I do wonder why it's doing that. But anyway, instead of sample, I guess for commands equals input split by char. And it says 434. It did run. All right, I can't not check. Local variables never used. Can it start? Can we just quit? Try again? No. Let's open. It's dot what? Cache? And then I can never freaking remember dot state, right? Dot local. Oh, why is it exiting? Do you think maybe the compile time code is exiting and that's exiting the compiler? Right, because if I run this, no, failed type checking with 2 errors. Oh gosh. Oh, less is going to be... Let's print less. Still crashing. It would print something though. I'm not printing the input anymore. Oh, I am. Variables never use sample. Day 1, 434. It doesn't exit. It works fine, and then it crashes here. Oh. Maybe it's like trying to open the same file again. Well, there we have it. Let's just do it again for fun. It's pretty fast. I mean, not that fast, but for compile time, bytecode executor, you know, we're getting there. Is it correct? Ooh. No. Just gonna look at my changes. Maybe we never hit 0 valid value. Yeah, right. That's the whole point. Well, I think I'm about out of time, so I'll have to finish this later today. Thanks for watching. Really appreciate it. This was fun. We'll see what I can do about resolving some of these mysteries too before I come back.